and today I will try to present briefly some of the grading components that we are developing for sensors and fiber lasers for wavelengths beyond 2 microns. So I will take the opportunity to say a few words about the Lumoscribe. As Antonio said, we are in the Cyprus. We are established in May 2018, so we are 7.5 almost years old. We are a small company of 6 people, including research and administration staff, which is specialized for the development of components in optical fibers, either for sensing or for laser applications. So we are a company which is growing organically, mostly through different national and private research projects, either from the local funding body or from the European funding agency. So one of the main concepts that we are interested as a company and we are working the last, let's say, 6 years is the mid-IR fiber lasers. And here we are defining the mid-IR region with the broader definition, let's say starting for around 2 up to 20. Why? Because for different reasons, very exciting application in many fields, gas sensing, biomedical, material processing, and so on and so forth. But as you possibly know, or most of you in the audience, these wavelengths are quite beyond the operational wavelength range of silica fibers. So different kind of materials, other materials, more exotic, let's say, should be used, like fluoride fibers and alkogenide and some other kinds of materials. So as a result, these materials are quite different in terms of optical, chemical, and mechanical characteristics. And especially when you are talking about monolithic fiber lasers, all the modifications that need to be performed to develop the component need to be highly precise to have usable components with the minimum losses. Need to mention here that with the monolithic term, we mean that the whole fiber laser, it is completely not using free space component, but all the components are inside the fibers. So starting with some components in silica fibers, using silica fibers, we develop high reflection gratings in thulium and holmium silica fibers. Here you can see some spectrum of the high reflectivity gratings and some chair gratings over there with a low reflectivity in order to create the fiber laser cavity. And when you characterize these fibers in the fiber laser configuration, we found something like more than 64% of slope efficiency for the thulium fiber lasers, and around 72% for the holmium fiber lasers, which when you compare these values with designs which were developed with gratings in passive fiber spliced with the active, we are talking about an improvement of around 50%. Need to mention here that these lasers was only dedicated for low to medium continuous wave fiber lasers. So on the same way, we proceed to more exotic, let's say, fibers, fluoride, indium fluoride, and Ziplan fibers. So we successfully create some high reflectivity gratings, fiber gratings in double cladding fibers and single cladding, and we develop a mid-IR fiber laser at 3.5 in collaboration with Mirage Photonics, Cyprus University of Technology, and the University of Adelaide in Australia, using a double cladding erbium dome fiber laser with a laser emission at almost 3.5, precisely 3.466 around nanometers. And it is a hybrid, let's say, design. So one reflector grating and the other is mirror, and it was pumped with a dual wavelength pumping method. And as you can see from the results, very nice laser lines and and a slope efficiency of around 50.2%, which it is almost double when you compare the same cavity using exclusively free space components. So this laser was used to measure acetone vapor sensing for this kind of application. So it was a simple setup, as you can see here, a reference arm, and the measuring arm. We have a chopper that will create these sine waves and compare using oscilloscope the difference between the two arms. So we achieve with this setup something like 1200 ppm per percentage for a single pass laser. But of course, this sensitivity can be significantly increased either by multi-passes of the laser or by tuning the laser to a lower wavelength, which is matching better to higher absorption, as we can see here in the figure of the NIST data. Another type of grading that we developed recently is long period gradings using Zipline fibers. So basically there are you can categorize this kind of gradings in two types according to the manufacturing process. So the first one, to make refractive index modification in the core of the fiber, and the second one is to mechanically induce some deformation, periodic deformation of the cladding at the core of the fiber. So the periodic, these structures satisfies the long period equation, and the light is matching to specific cladding modes. So using a filament process and splicer, we very well control the dimension, the diameter of the waist and the diameter. So we were able to have a control, let's say, periodic structure of minimum around 180 microns. And as you can see from the figure here, it is very consistent as a methodology. So for each period, we have a constantly 3 to 4 dB increase in the spectrum per period. So this setup was characterized in terms of loss, and we end up something like less than 0.8 dB. And this is very useful as application in fiber laser, but also for sensing, because especially the second method, when controlling the waist diameter of this component, basically the light in the core of the fiber having higher access to the ambient refractive index, and can be very useful for liquid sensing or any refractive index changes. An example that this is a spectrum that we had. So we have a 3 LPG peaks. Let's focus on the third one. We characterize for temperature. We end up something like almost 6 nanometers of shift per degree Celsius, almost double when compared to common silica slopes or calibration curves. But the most interesting thing is when you compare the result for refractive index values, which belong on the region of 1.48. In this region, because mostly of the refractive index of a Zipline as a material, which is around 1.51, we had a sensitivity of something like 1400, more than 1400 nanometer for refractive index unit, which is quite high for just an LPG without any other materials included around it. So more or less, this was a brief introduction of what we are doing in the company, what we did, some of the topics that we did. We are a company that have an expertise on the development of this kind of gradings. And we have some experience of, let's say, 6 years on these exotic materials. And to answer the question that Antonio possibly will ask me in a while, what can you do? I just answer, what can they do for you? We think that it will be fruitful for us to find strategic partners and or collaborators, help us to commercialize in the future this technology and work together to improve these components for future high power mid-IR fiber lasers. So that's all from me. Thank you for your attention. And if you have any question, I will try my best to answer.